In this video, I will go step by step through a multivariate unconstrained optimization problem. In some sense, the steps required here are very similar to a univariate problem. You will first have to understand the domain of your function. You will then have to calculate first order partial derivatives and then also the second order partial derivatives. We can do that at the start. We know we need them. Then you use the first order partial derivatives and find the stationarity points by setting the first order partial derivatives to 0 and then solving for the arguments that make the first order partial derivatives equal to 0. Then you have stationarity points and you need to investigate the local properties of these. And you do that by checking the values and the properties of the Hessian function containing the second order partial derivatives. So examining the properties of the Hessian at these stationarity points. That would tell you whether you are dealing with local maxima, local minima, or saddle points. Then you want to know whether the local optima, or whether amongst the local optima there's perhaps also a global optimum, either a global maximum or a global minimum. If you're fortunate enough that you only have one stationarity point, you can check whether there are sufficient conditions for that one local either maximum or minimum to also be a global maximum or minimum, whether the sufficient conditions for that are given. If you have more than one stationarity point, you don't even have to check, because then for sure these sufficient conditions are not met. If you have several stationarity points, perhaps even several local maxima or several local minima, what you will then have to do is you'll first check which of your local maxima gives you the highest value and which of your local minima gives you the lowest function value. And these are now your candidate or potential global maxima and minima. And then you will have to understand how the function behaves at the edges of its domain to see whether you can find areas of the function where the function value either goes beyond the maximum value or below the minimum value of your candidate global optima. So these are the steps we will go through in this following example. So here's our example function. It is a function which is cubic in x1 and quadratic in x2. So we're having two arguments to this function. The domain of this function is such that it is defined across the real domain in both dimensions. So we said the first step we want to do is we want to calculate the first order partial derivatives. So f prime 1, meaning the first order partial derivative with respect to x1 is 3x1 squared minus 3. And the first order partial derivative with respect to x2 is just 2x2. And let's already calculate the second order partial derivatives. You don't need to, you could find stationarity points first, but I like doing that. So the second order partial derivative with respect to x1 and x1, we're finding the partial derivative of that first order partial derivative with respect to x1 again, and that is 6x1. Then let's calculate the second order partial derivatives 1, 2. So we're taking again that first order partial derivative, but now the partial derivative with respect to x2, and that's just 0 because x2 doesn't appear. Then the second order partial derivative 2, 2. So we're taking this one here and finding again the partial derivative with respect to x2, and that is just 2. And then the second order partial derivative with respect to 1. So we're taking that second first order partial derivative and finding the derivative with respect to x1. There is no x1 in here, so that is just a 0. That means from this we can already see, we can write down the Hessian function, which is potentially a function of x1 and x2, and that is 6x1 and 2 on the diagonal and 0 on the off diagonal. So let's find the stationarity points, and we find those by setting the first order partial derivatives, or the gradient vector, if we collected that in a vector, to 0. Now in this case, this is fairly straightforward to solve. It's really easy for x2 from the second order partial derivative, because we can see that x2 is equal to 0. Now, from the first order partial derivative, that's a quadratic function in x1, so we get potentially two solutions here. And we can just calculate, we bring the 3 onto the other side. X1 squared is equal to 3. Then we can divide this equation by 3. So we'll divide by 3, and what we then get is, whoops, and so that 3 goes away, and that 3 turns into a 1. So let me do this here. So from f prime 1, we get x1 squared equals 1, and that means we know that x1 has two solutions. It is either 1 or x1 equal to -1. So it's obvious from here that we have two stationarity points. Okay, so we're getting two stationarity points. And there, let's call that point A is a point where for both, I should start like this. For both points, the second coordinate is 0, because for x2, we only have 0. But for x1, we have 1 and -1, so one stationarity point will be at 1, 0, and the other will be at -1, 0. Let's just give them names, points A and B. So we know our two stationarity points, and these are all stationarity points of that function. Now we need to figure out whether they are local minima, maxima, or saddle points. And to do that, we need to calculate the Hessian at these points. Actually, what we first do is we calculate the function value. So let's just calculate the function value at point A. And the function value at point A, so if we substitute the value 1 and 0 into our original function, let me just highlight what our original function is here. So we're substituting 1 and 0 into this. We're getting -1 minus 3 times, where are we here? Oh no, sorry, we're substituting 1 and 0. So we're getting 1 cubed is 1 minus 3 times 1. So we are getting -2. And the function value at point B is, let's do that pedestrian way, -1 to the power of 3 is -1 minus 3 times -1 plus 0 squared. So here we are getting -1 plus 3, -1 plus 3, which is 2. Okay, so we already know point B is certainly higher than point A. That by itself possibly already tells us that B has to be a local maximum, or one of them. Actually, let's find out. It's actually not so straightforward. So next, what we want to know is the function at point A, is it concave, convex, or neither, in which case it would be a saddle point. So to do that is we're plugging in our function, our coordinates into the Hessian. So h at A, at point A, meaning at coordinates 1, 0. So h is a function here. So 6 times 1 is 6. And the rest, so you see when we calculate the Hessian here, let me use a different highlighter here. The Hessian only has one value, the 1, 1 element that changes with the argument. everything else in that Hessian is constant. Right? This value, and this value will always be the same. So that's 6 times x1 for our point A, that is just 6. And the rest is the same, 0, 0, 2. And let's write down the Hessian for B before we continue. The Hessian for B is 6 times x1, so that is negative 6. And then 0, 0, and 2 here. What we need to figure out whether the function is concave or convex at this point is we need to figure out whether the Hessian at that point is either negative definite or positive definite. If it's neither, we will have a saddle point. So what about h at A? So h at A, the determinant of h at A is equal to 6 times 2 minus 0. So that is 12. The Hessian, the determinant of the Hessian at point B is equal to negative 6 times 2 minus 0, which is negative 12. So importantly, what we need to know, what we are really only interested in the determinant, is how it is relative to 0. So here, HA is positive definite. And that is because we have a determinant larger than 0 and our diagonal element is positive. What about HB? HB, well, we have a negative determinant. If you have a negative determinant, you immediately know that the Hessian here is indefinite. So what does that tell us about the points H and B? Well, if the Hessian is positive definite at point A, then we know from here that A is a local minimum. And if the Hessian is indefinite at point B, we conclude from here that B is a saddle point. So that is brilliant. We've learned a lot already about this function. We have 2 stationarity points. One is a local minimum and one point B is a saddle point. What we now want to figure out, I'll just divide this page and we'll continue here on the right-hand side, is point A also a global minimum? It's certainly a local minimum. Is it also a global minimum? The sufficient condition for a point, for a stationarity point, which is a local minimum, to also be a global minimum, is for the function to be convex everywhere. We know it is convex at point A, because at point A, the Hessian is positive definite. So at that point, the function is convex. However, at this point here, at point B, we found the function, or we found the Hessian to be indefinite, which means that in some direction it's convex at this point, and in another direction the function is shaped concavely. So at that point it's neither convex nor concave, but not flat either. So we already know that this function isn't convex globally. So we don't really need to check it. The way how you would check it is you would go back to your Hessian, and you would have to wonder whether for all possible values of x1, because that is the argument that plays into Hessian here, that Hessian would be positive definite, or at least positive semi-definite. That means we cannot have negative determinants, but we already know that we found a negative determinant down here at point B. So we don't really need to check that condition. We know it's not given. So from now on, we need to understand the behavior of the function, basically around its domain. Let me just draw a little graph as if we were drawing sort of contour plots. And let's say x1 is here, x2 is here. And we know our two stationarity points, and let's put that in one in red, the local minimum. That was here. That was point A at 1, 0. And we had a second stationarity point that was our point B. That was at -1, 0. And that was a settle point. Point A was a local minimum with a function value of -2. Should use that in red. -2. That was our function value here. So we now basically need to check whether anywhere in the domain the function value will drop below -2. Because if that was the case, point A would not be a global minimum. So we're now going to figure out, for starters, how does the function behave, perhaps if we move along this direction in the domain, or along this direction, or perhaps along this direction, along this direction. So let's figure out, if we were to move along that axis, along which x2 would continue to be 0. Let's say this is the origin, so we have 0 here. If you look at your function, we're having x1 cubed minus 3x1. And then the x2, as we walk along here, will just be 0. So we're having x1 cubed minus 3x1. If we are increasing x1 ever more, that value will just go to infinity. So as we go along here, the function value will go to infinity. What about if we go this direction? So we're keeping x2 at 0, and we are decreasing x1 to -infinity. So we're getting a very large negative value, cubed. That will still be very large, negative, because cubed, minus 3 times something negative. So that part will now be positive if x1 is negative, but that x1 cubed will totally dominate this function for large numbers. So if we are decreasing x1 towards -infinity, the function value will also go to -infinity. Of course, you could confirm that by just checking with a few values. Say x1 equals -10, -100, -200, and you would just quickly see that this function goes to -infinity. So at this stage, we are basically finished. And why are we finished? Well, the question was, at this point A, the function value at point A was -2, and that was a local minimum. But we have found a direction in the domain of the function along the x1 axis towards -infinity, where the function value will go to -infinity, so it will drop below -2. So we already know from this that point A is not a global minimum. So in fact, this function has neither a global minimum nor a global maximum. They would have to be found amongst our stationarity points. We didn't even find a local maximum, so there was clearly no global maximum. We found a local minimum, but we just established that this local minimum is just that, only local minimum, no global minimum. You could also, just for exercise sake, we can see how does the function behave in this direction and in this direction. So if we set x1 to be equal to 0, and we are just increasing x2 towards infinity, then we are really only looking at this last part here, because x1 we kept to 0, And you can perhaps see that then the function value will go to infinity here as well. And what if we move x2 to negative infinity? Well, it's going to be a very largely negative number, so very small number squared. That will also go to infinity. So here the function will also go to infinity. We already solved the problem, but you could also think about how does the function behave in this direction, or in this direction, and in this direction. And you would use profile functions to do this, but I'm not going to do this here. So we are finished. The problem is basically solved. This function has a local minimum and a saddle point, and that's it. Let's see whether everything we've learned chimes with how the function really looks like. I prepared a graph. So here is the graph for the function, plotted nicely, and our 2 points B and A indicated. A was at 1, x1, 1, and x2, 0. Okay, that was the value. That was our local minimum. And B was at -1 and 0. So that was here. That was a saddle point. And here you can perhaps see a saddle point. Yes, it looks like a Pringle. We have in the x2 direction, you can see that the function is convex, but in the x1 direction, along this axis, the function behaves concavely. It's really quite beautiful. So we've done everything right. Perhaps you could imagine, once you just saw this picture, what the function looks like, but I actually think this is quite difficult, okay, to imagine these shapes. But we didn't need to know that. By just investigating how the function behaves into the directions in the domain, we could solve the problem.